So I have a few things to say before I start the talk. I'll see if I can remember them all. First, thanks very much to the organizers for the invitation and for the really great thematic program. It's been a pleasure being here. So the second is non-mathematical. It's about my sister, who's a professional cellist and is, in my opinion, much more talented at what she does than I am at what I do, and probably works harder at it as well. She has a project in honor of the 100th anniversary of the composer Zoltán Kodály, which involves a tour of his solo cello sonata and four new pieces she's commissioned by composers in honor of the 100th anniversary. The tour will be followed by a recording of an album titled Scordatura. Presuming she can raise the remaining funds to make this happen. So there's quite a nice video you can watch of with more information about the project on Kickstarter. I won't show that to you now because I don't assume that this will interest all of you, but I hope it will interest some of you. So the third thing I wanted to say before I start the talk is, for those who may not have heard, that we're organizing a summer school in probability. Some of the other organizers are in the room. This is the 8th, I believe, in the series of PIM summer schools in probability, which have been a great success and are quite well known, I'm sure. This one is being held in Montreal from June 15th to July 11th of this year. And the main courses are being given by Remco van der Hofstede and Alice Guionnet. So if you or your students are interested in that, I encourage you to register and attend. All right, so on to the talk. It's very nice to be giving this talk here because in some way the story of canonical embeddings of planar maps starts in Cambridge. With some work of 4 talented undergraduates in 1940, and that's part of this story. So maybe I'll just say a little bit about this drawing before we get started. So it's impossible to see, but right about where this red dot is, there is a red dot. And still, it's still there, but I think only I can see it. And this drawing is contained within that red dot on the right, if you zoom in. So this is an object with some very nice self-similar fractal properties. Okay, so I guess the theme of this workshop largely relates to this very sort of story. A reasonable model for a uniformly random discrete surface is a random map on the sphere, and we now understand that there's in some sense, a continuum analog of this uniformly random continuous surface. I'm sure you all recognize the bottom image by now. So this continuous limit is called the Brownian map, which we'd maybe like to think of it as a random distance function on the sphere. But in fact, it's not quite that. It's a random equivalence class of metric spaces, and that limit is somehow almost surely topologically a sphere, but it doesn't come canonically represented as a metric, random metric on S2. There's many possible representatives of that form. As Asaf said in his talk, nobody's perfect except. When Jean-François says that we would like to have a canonical construction of a random metric on the sphere S2 in such a way that the Brownian map has the law of S2 delta, we really would like that. And we expect to be able to find such a thing that will somehow behave nicely under conformal transformations of the sphere. So this is the kind of motivation that leads one to study canonical embeddings of maps, because maybe if we can canonically embed the maps, then we can pass that through to the limit and obtain a canonical representation of the limit. So far, we've had much more success doing that in the sense of local limits than in the sense of compact limits like the Brownian map, and my story is not an exception to that rule. Okay, but I think that this is an important motivation nonetheless. So we've heard more so far this week about canonical representations via circle packings, right, where this drawing represents a planar map by viewing the vertices as circles, say put a dot at the center of each circle, and join two circles by an edge, join two dots by an edge if the circles are tangent. Okay, so this is a canonical representation of a simple triangulation in a geometric way. And Jean-François has a sort of concrete conjecture about this particular family of canonical representations, also from his ICM Proceedings article. So basically what this says is we should be able to sort of couple these circle packings in such a way that the first condition essentially says that the circles become dense in the sphere in S2. Okay, so you can't find sort of a center that's macroscopically separated from the nearest other center when n is large, and if you sort of look at the natural continuous interpolation of the graph distance for the centers as a distance function on right. So we've drawn this graph corresponding to a circle packing on S2. If we rescale the graph distance and sort of extend that to the sphere in a natural way, that should give us a continuous random process, which would be then our canonical representative of the metric of the Brownian map. Okay, so this work is not about circle packing, as the title suggests. It's about canonical embeddings via squarings. And and it's also about another aspect of this story, which is coupling random maps of different sizes. Okay, so here you'd like to somehow couple them in such a way that the compact limit behaves nicely. Mine will be about a sort of explicit coupling such that a kind of local limit, which is represented as a compact geometric object, but is nonetheless a local limit, behaves nicely. Okay, so let me start by trying to convince you that you understand how to draw maps as squarings with a bunch of pictures. Okay, so how do we turn? So our maps, by the way, will always, so they're planar graphs properly drawn in S2. They're going to come equipped with an oriented root edge, as you'll be familiar with. And my convention will be to draw that root edge so it's incident to the unbounded face. Okay. So This is a particularly unilluminating example. The squaring that represents a single edge is a single square. Okay? The squaring that represents two edges drawn in series is two squares stacked one on top of the other. Okay, and I said that there's a root edge ST, okay, which I'm not drawing in it, and I will frequently omit it from the drawing because in the calculation of these squarings, it's common to remove that root edge before you continue with the drawing. Okay, here's a slightly more complicated example, but you can still, I expect, see a sort of parallel between the drawing and the graph. So here we have a path of length 3 between S and T, but we have 3 copies of the first edge, 2 of the second, and 3 of the third. That gives us a squaring with 3 squares stacked on top of 2 squares stacked on top of 3 squares. Okay, at the very least, you can somehow see that in these drawings, edges correspond to squares just by counting. Okay, let's do some, and maybe I can point out at this point that vertices correspond to lines in some way. Okay, so here we have a horizontal line which is going to correspond to this vertex, some edges above it, some edges below it. Okay, so this is not terribly rigorous yet. But let's keep going with the examples before I tell you the sort of proper mathematical formalism. This is the planar dual of this graph. Okay, so if you put a vertex in each face, remember there is an edge ST which I'm not drawing. Okay, if you put a vertex in each face, then and draw the dual edges, then there will be one vertex on the left of this graph, one on the right, and they'll be joined by a path of length 3 through here, path of length 2 through here, and a path of length 3 through there. And that's precisely what we see here. Vertices S and T with paths of length 3, 2, and 3. Okay? And indeed, in this drawing, you sort of have a 3 stacked squares, 2 stacked squares, 3 stacked squares. But the point that I want you to notice is that this drawing is just this drawing rotated by 90 degrees, if you like. Okay, so for this sort of geometric representation, planar duality is going to correspond to a rotation by pi over 2. And maybe one final example where things are starting to get a little bit more complicated, but you can still kind of see the parallel between the geometric and the graph structure. Okay, so how do we turn this into a general procedure for drawing a squaring if we're given a planar map? This was figured out by Brooks, Smith, Stone, and Tutt in 1940 when they were all undergraduates at Trinity College, I believe, Cambridge. So if we're given such a planar map, we can define a squaring of a rectangle as follows. So I'll just describe the procedure to you. Here's our map, and here I have drawn this root edge ST in the unbounded face. So I'd like you to think of removing this edge ST, and then put potential S1. So we're going to view this as an electrical network where edges have unit resistance. We put potential 1 at S, and we ground the network at T. Okay, so if you like, there's actually a battery along the edge ST that's putting current through the system. So current will flow, and to describe that current, we're going to write PV for the potential at a node V and CE for the current through the edge E. Okay. So P of S is 1, P of T is 0, and we don't know how much total current there will be because we don't know what the effective resistance of the network is. Okay. Now for each edge of the network, we'll make a square whose side length is the current through the edge. Okay? And the story is that all those squares will fit together to form a squaring. And one way to just explicitly describe the positions of the squares is that they're, let me back up. So the vertical positions of the squares can be deduced from what I've already told you, because if you look at a given edge, the vertices that are the endpoints of that edge have potentials, and those potentials should be the heights of the vertex, the heights of the vertices. So the square then should have a top border given by one of the potentials and a bottom border given by the other potential, and the difference in those potentials is precisely the current through that edge. Okay, so that tells us that our rule for the height is consistent. How do we decide the horizontal location of the square? Well, we use the dual construction and this fact that I sort of alluded to, that the dual and the primal squarings should be related by a rotation, to say that somehow the horizontal position of the squares should correspond to a vertical position for the dual squaring. And so we can just use the dual squaring to define the horizontal position by these rules. Okay, so as I said, the vertical borders are given by the potentials of the vertices at the end of the edge UV, and the horizontal positions are given by the potentials at the endpoints of the dual edge U star V star. Okay, for this to work, you need to, in the dual construction, you push current 1 through the network instead of putting potential difference 1 between the endpoints. Okay. So let's just examine this and see that what I just described is sort of what's going on. I should have said, I knew I'd forget something at the start. Feel free to stop me if you have questions. So I want to just examine this together for a minute. So in this drawing, again, horizontal lines are corresponding to vertices of the map. Okay, and so and I've drawn the map here so that the height of the vertices is precisely the potential of the vertices in this electrical network. Okay, so vertices higher up in the drawing have greater potential. So in particular, this vertex has greater potential than this vertex, and they're joined by an edge, so that means that current will flow from top to bottom. And that current, how much current? Well, that's just described by this square here. It's the potential difference between the endpoints. Okay, so current is outgoing from this node to this node and this node. That corresponds to these two squares. And incoming from S, which corresponds to this square. Okay, similarly, here we have a node that will have incoming current along 2 edges and outgoing current along 3 edges. Okay, and that corresponds to this line here, which has 2 squares above it and 3 squares below it. Okay. So just without giving you a formal proof of anything, sort of some intuition for why it's plausible that this always will work. Well, this is just sort of telling you that at least some various aspects of the construction are consistent. Okay. One is that, so Kirchhoff's, we're going to just use Kirchhoff's laws, the first of which says that flow in equals flow out, right? And that says in the drawing that given that the total flow in is just captured by the sum of the side lengths of the squares sitting above the line, and the flow out is the sum of the side lengths of the squares sitting below the line, that those two quantities will be equal. Okay? So the squares above and below a line have the same total width. That's good if we want to have a consistent drawing. Okay? And the cycle law tells us that we can determine the height of a line by summing the potential differences, or equivalently the side lengths of the squares along any path to the vertex, and we'll get the same answer. Okay. All right. I'm going to continue talking about this construction a little bit more, but if there's something that's bothering you, feel free to stop me in the next few slides. Otherwise, yes.
How do you see that these are squares?
How do you see that these are squares? That's a good question. So you have to, you have to write down a computation which is not too hard to see that that when you put current 1 in the dual network, you'll get the same current through each edge as if you put potential difference 1 in the primal network. But that you can view that as a statement about the probability that edges are in the spanning tree of the primal or not in the spanning tree of the dual, and it's not very hard to see. Okay, so we've seen these examples. Here's this one again showing you the connection between primal and dual. I'd like to mention that, so here's 2 examples of kinds of degeneracy in the network in a way. You can have 2 parallel edges. In a way that corresponds to a rectangle, okay, 1 by 2 rectangle, or 2 series edges corresponds to a 2 by 1 rectangle. Maybe I should have, anyway, up to rotation. And this whole construction makes sense for networks with resistances. Okay, and what happens is that if you have that, so resistance corresponds to aspect ratio. Okay, low resistance edges give you flat rectangles. High resistance edges give you tall, skinny rectangles. Okay, another thing I should mention is that any time you see a subnetwork which is connected to the rest of the network by at just 2 nodes, there'll be some flow in and flow out of that subnetwork, but we can certainly just view this as a single resistor with a given effective resistance between its endpoints. And so this drawing in the squaring is going to look like a rectangle with a given effective resistance. Okay, it'll be a rectangle with a given aspect ratio. Okay, and so these sorts of subnetworks somehow correspond to a failure of irreducibility in the drawing. You can find a non-trivial subsquaring, which is not the whole network. Okay, so in the original paper, I believe it was in the original paper of 1940, they called a squaring irreducible if there were no structures such as this. And what you see here is that being irreducible, so if you can find a non-trivial 2-cut in your map, 2 vertices that separate the map into non-trivial connected parts, then your network, then the associated squaring will be reducible. So irreducible squarings somehow correspond to 3 connected planar maps, and it's 3 connected planar maps on which I'm going to focus for most of the rest of the talk. They're kind of the building blocks. Okay, the last comment about these squarings before I tell you our result is that the procedure is not reversible. Okay? Because squares can vanish because edges in a network might have 0 current through them. So in this example, right, if you look at this squaring, it looks like a node with 2 wires coming out of it connected to a node with 2 wires coming out of it connected to a node. That's this drawing here. But I could equivalently separate this node in 2 and have 2 disjoint paths of length 2. I would get 2 nodes that were equipotential in my network. Okay, and that would be saying that really I could view this as 2 lines instead of 1. And I could even join an edge between them because they're equipotential, no current will flow, it won't change the network. Okay? So there's a failure of invertibility that comes from a certain kind of, you can think of it as a symmetry in the network. It's when you have 2 equipotential nodes on the same face. Okay? And we suspect that for typical large networks that does not occur with high probability, but we can't prove that. So, okay. So what can we do with all of this? Yes?
I'm sorry about the reducible network, about the reducible squarings.
Yes.
So, that doesn't correspond to two-connected graphs, because if you remove this, here you can remove one vertex such that it stops being connected.
No, I'm thinking, remember that this eventually connects to a node T down here, and this eventually connects to a node S up here, and S and T are joined by an edge.
So may I ask a question? When you are computing the flow, you assume an equal resistance in each of the links.
If you, yes, so at the start of this construction, whoops, I'm going backwards. At the start of this construction, I was assuming that all edges had resistance exactly 1. If you do it with more general resistances, then you will not get squares, you'll get rectangles with various aspect ratios. But they will still perfectly tile a rectangle. Okay.
There's a dual. In general, here's what to do. How to construct a dual when you get actually.
You have to take the resistance to be 1 over the primal resistance. Okay, so any other questions about the squaring construction itself before I tell you what we do with it? Okay. So what we do is construct growing sort of an explicit coupling of a sequence of growing planar maps. Okay, say with the nth having n edges, maybe it's n plus 4 actually, but obviously that doesn't matter. So these maps will converge almost surely in the local sense. So if you fix, they're going to be rooted at an edge, and if you look at a ball of any finite radius around that root edge, then it's eventually constant once n is large enough. The limit is the uniformly random infinite 3-connected planar map. The associated squarings converge almost surely for the Hausdorff distance to a limit s infinity, and that limit almost surely has exactly 1 accumulation point. Okay, so there's a few asterisks on this slide. Let me explain what they're there for. The first is just to explain what this number 3 means. It means that if you take another sequence, call it Hn, where Hn is a random 3-connected rooted planar map with n edges, then Hn converges in distribution in the local sense to this same limit g infinity. Okay? So this object is the distributional limit of large random 3-connected maps. The reason that the theorem stated this way is because our maps Gn may not be 3-connected. Sometimes they'll somehow just fail to be 3-connected because of some local defect, but they're almost 3-connected, and in the limit that defect vanishes. Okay, so I'll explain that a little more as we go. Statement 4 is just to say if, without being too formal about it, that another way of saying this in our setting is that the position and size of each square stabilizes as n gets large. So for any edge in the network, that edge is present in Gn for all sufficiently large n because the graph stabilizes. And so you can talk about the position and size of the corresponding square, and that those quantities stabilize for all n, for all edges. And the last statement rules out a couple kinds of degeneracy that could occur in the limit. Okay, so when you take this limit, there are two things you don't want to happen. One is, if Sn was the squaring, which was just the n by n grid squaring of a unit square, then this would converge to, I mean, in the Hausdorff sense, the sort of compact representative of this in the limit is just a black square, a fully filled in square. Okay? That's not a terribly interesting limit object. So one thing that this says is that doesn't happen because there's only one point of accumulation. Another thing that doesn't happen, remember we said that some edges can vanish because no current flows through them. Okay, so in general it's possible that Sn has fewer than n squares even though Gn has n edges. And you can imagine that there's so much degeneracy in the network that in fact the limit only ends up with finitely many squares. Okay? But that also doesn't happen. That's a very weak statement, you know. All I'm saying is that the number of squares is tending to infinity with the size. Whereas we believe that with high probability the number of squares is equal to the number of edges. But at least we can rule out that all but finitely many edges receive current 0 in the limit. Okay, so I've already sort of explained this connection between squarings and graphs, so I'm going to spend most of the rest of the talk telling you about this coupling, this explicit growth procedure for random planar maps that we've built. So before I move on to that, are there any questions about the statement of the theorem? Yeah.
So, you're saying in the three connected case, there's no local configuration that guarantees zero current across an edge?
No, because there are three connected planar maps that have a non-trivial symmetry that exchanges two vertices on a face, and then those two vertices will, I mean, if you put or don't put the edge between them, it doesn't change anything.
So that does show you that there's a positive density of vertices that don't appear in the map, in the squaring, right?
Positive density of vertices that don't appear in the squaring.
Yeah, I mean that are where the square is degenerate. I mean, if it can happen in the map, then it will happen, right?
It's possible that some sort of rerouting invariance would yield what you said. I'd have to think about it in whether that carries through the limit. I don't want to hazard a guess on air. Okay, so here's how the growth procedure works. So we already saw this connection between squarings and maps. Next, I'll use Tut's bijection, which we've already seen a couple times this week, to study, instead of maps, study irreducible quadrangulations. So how does Tut's bijection work again? We put a vertex in each face of our map. We join those vertices to all of the corners incident to the corresponding face, and it gives us a quadrangulation. You get along each edge, well, let me pick a better edge. Along each edge, you end up with two little paths of length 2 in black. So that gives you a quadrangulation. And this word irreducible is connected to the previous irreducible. Okay? So it turns out that two cuts in the map correspond to, you think about what will happen if you have a region of the map which is separated by a 2 cut from the rest of the map, then in this dual drawing you end up putting a vertex on one side, it'll be joined to these two corners, a vertex on the other side that's joined to these two corners, and then some more stuff inside. Okay, so this is a path, this is a cycle of length 4 that is not a face. Okay? And a quadrangulation is called irreducible if this never occurs. Okay, if every cycle of length 4 bounds a face. Okay, so irreducible quadrangulations correspond to 3 connected maps. Okay, and so we'd like to study irreducible quadrangulations. What we end up studying is not quite irreducible quadrangulations because we allow there to be some defect around one face. And that's because we use a lovely bit of work by Eric Fusy, Dominique Poulalon, and Gilles Schaeffer, which gives a bijection of the sort of blossoming family that Marie described and Gilles further discussed, between uniform binary trees and irreducible quadrangulations of a hexagon. I'll explain what I mean in a second. Let me briefly go through this procedure that associates quadrangulations with binary trees. It goes like this. Got it? Let's do it again a bit more slowly. So here's our binary tree. We want to make sort of closures in this clockwise sense that create squares, cycle faces of degree 4. So we're going to do that by taking leaves of our tree and gluing them into corners of the map. Okay, and we do it in a greedy way in the clockwise order. So whenever we see a way to glue a leaf to make us a face of degree 4, we do it. Okay, we keep going around until we can't do it anymore. And it turns out that it doesn't matter where we start. We always get the same answer. And let's see how that goes. So you see, here I can make a face of degree 4. Once I do, here I can make another face of degree 4. Here I can make a face of degree 4. Here I can as well. And that's all. I haven't quite finished with all of the leaves. So I have some sort of quadrangulation with an unbounded face that has some dangly bits, some things that were originally leaves of the tree. Okay? So the way I finish this off is I draw a hexagon around the whole drawing in the unbounded face. And I join up these remaining leaves to the vertices of the hexagon to create some more faces of degree 4. So here I can make a face of degree 4, 1, 2, 3, 4. Here I can make another 1, 2, 3, 4, and so on. Okay? And some simple combinatorics tells me that this will always work out. And if I don't have if I don't have labeled vertices on the unbounded face, then there's only one way to do this. So there's no there's no degrees of freedom here. Okay, I join all these up. Now I have a map in which every face, you need to view these red connections and the black connections as a single edge. So this is an edge, this is an edge. These are edges. This is an edge, this is an edge. Okay, so in this map, every face has degree 4 except the unbounded face, which has degree 6. So this is a quadrangulation of a hexagon. And it is irreducible in the sense that all of the degree, any cycle of length 4 bounds a face. Okay. We end up rooting this at to make this a full quadrangulation, we add an edge to the unbounded face to split the hexagon into 2 faces of degree 4. And this can create degenerate cycles of degree 4. This can break irreducibility. Okay? But it only breaks irreducibility locally near this unbounded face. And you can explicitly quantify sort of the degree to which it can break irreducibility by sort of an analog of appealing argument in a way. I mean, it's not really appealing argument. It's just sort of you have to keep stripping things off of the unbounded face until you get rid of the degeneracies, and that doesn't last for very long. It's sort of explicitly described in this paper. Okay, so this tells us that if we can grow binary, because these are all bijective procedures, or in this latter case it's a 3-to-1 procedure, but it's, it's sort of a uniform push forward of it'll give you a uniform push forward of a uniform measure. So if you have the uniform measure on binary trees, it'll push forward to the uniform measure on these irreducible quadrangulations, then by Tutt's bijection to uniform measure on the associated class of maps, whatever that is. Okay, if they were genuinely irreducible, it would be 3 connected maps. They're not quite, but So we'd like to find a procedure then. Remember, we're trying to grow the maps by some explicit stochastic process, and so we'd like to, backing up through here, just grow the trees. Find an explicit growth procedure for uniform binary trees. Whoops. And there's a beautiful paper of Malvina Lučák and Peter Winkler, which explains how to couple the uniform measure on binary trees with n leaves for different n. Okay. And I'd like to explain that to you. So the picture is this. We have a binary tree. So this is with n leaves. We'd like to get a binary tree with n plus 1 leaves that contains the one with n leaves. Okay, so all we can do is pick a leaf and decide that's no longer a leaf. It's going to be an internal vertex. So we grow it a leaf. Okay? Because we want to have a nested sequence of trees. This is the only way you can grow from n to n plus 1 leaves. All right? So one thing we could do is just always pick a uniform leaf and grow it that leaf. That would give us a stochastic process on binary trees. Okay? But it would not have uniform marginals. So if you look at if your rule for growing is pick a uniform leaf and grow it that leaf, then that induces a distribution on trees with n leaves, binary trees with n leaves. And it's not the uniform distribution. And a simple way to see that is to compare these two trees. So one is a sort of caterpillar with n leaves, and the other is a complete binary tree of depth log n. So if a growth procedure which always picks a uniformly random leaf is going to grow this one, then it had better always just pick to grow on the right. Right? So it has probability roughly 1 over n factorial of doing that, because once it's grown the path, if it's going to keep growing the caterpillar, it had better just grow on the top, maybe 2 to the n over n factorial. But actually the plane structure matters, so it's like 1 over n factorial. For this drawing, on the other hand, there's all sorts of different orderings by which we could grow this, right? So there's far more than 1 over n factorial ways to grow this tree. So growing at uniform leaves, in fact, it corresponds to the random binary search tree procedure, which does not grow uniform trees. We need to do something else. This is what Lučák and Winkler figured out. So what are we trying to do? We're trying to push forward the uniform measure from the set of binary trees with n leaves. I haven't drawn, by the way, you see my leaves are square. I haven't drawn the leaves in this picture, just the internal nodes to keep it a bit more legible. So off of this, for example, there's 2 leaves there and another 2 leaves there and 1 leaf there. Okay, so we want to push forward the uniform measure from the set of binary trees with n leaves to the set of binary trees with n plus 1 leaves. These sets are just counted by Catalan numbers. Okay. And the sort of key idea is the following. We're just going to try to decide whether we should grow at a leaf that's on the left side of the tree or on the right side of the tree. Okay, we'll try to make that first decision. So how should that decision be made in a consistent way? Well, the uniform law behaves nicely under restriction. If I tell you that there are k leaves on the left, then the tree I see on the left is equally likely to be any binary tree with k leaves. So if I can consistently decide which side to grow on, then by induction, on the left I see a smaller tree, fewer leaves, so I can inductively apply the rule that I already had figured out to decide how to grow that left subtree. So if I can consistently choose which subtree to grow in, then by induction I can grow these trees. And to choose which subtree I should grow on, okay, all you have to do is just think for a second about how a given tree up here could have arisen from a tree down here as a function of the split at the root, this number of leaves on the left and on the right. So if my tree looked like this, it had one leaf on the left and n minus 1 on the right, then, or let's say n on the right, so this is where I've ended up, my tree with n plus 1 leaves, then I'd better have come from a tree that had one leaf on the left and n minus 1 on the right, and I chose to grow on the right. That's the only thing that could have happened. Okay? So I'm fully constrained if I see this split at the root in terms of the kinds of trees I could have come from. Okay, so that says that the total measure of trees like this, with one leaf on the left and n minus 1 leaves on the right, had better be at least a larger proportion of all the trees with n leaves as trees like this are among trees with n plus 1 leaves. You know, if trees with this split have probability 1%, I'd better have probability at least 1% of seeing a tree like this because I had to come from a tree like this. Okay? So that gives me an inequality that has to be satisfied in order for this push forward of the uniform measure to be possible. Okay? Now let's think about where trees that look like this can end up. Well, they either end up looking like this, or they end up looking like this. Right? If you see a tree that has 1 on the left and minus 1 on the right, you're going to end up with a tree that has one of these two splits. So if you look at the probability you see one of these two splits, up here it had better be at least as big as the probability you see this split down here, or else you just can't push forward all the measure you need to from trees like this. Okay? So if you can write down exactly the same thing more generally, where you start with k and n minus 1 on the right and ask or n minus k on the right. And that corresponds, if you group the trees according to their split at the root, to a condition on that's encoded by this bipartite graph. Right? What you're interested in doing is defining a flow on this bipartite graph that pushes forward the appropriate probabilities to each group of trees according to their split at the root. And these are the conditions. It says if I start with, if I end up with at most k minus 1 leaves on the left, then I must have come from something with at most k minus 1 leaves on the left. And if I start with at most k leaves on the left, then I must end up with at most k plus 1 leaves on the left. So you get two sets of inequalities, which you can just verify straightforwardly. And they tell you, they tell you that a flow exists in this network, satisfying the properties that you want. Okay? So this was a clever insight of Malvina Lučák and Peter Winkler that was the start of a more general paper where more general result where they showed that in fact you can grow uniform d-ary trees for any fixed d. Okay? And using that, it's maybe worth mentioning that it's actually not too hard to deduce that one can grow the sorts of trees that are used in any of the common bijections for maps. So you can grow uniform plane trees. You can grow the blossoming trees that Marie and I used to study simple triangulations. it's quite straightforward to see that all of these grow, and so you can couple these families of more or less whatever kind of geometric embedding associated to any of the geometric embeddings that people have looked at so far. Okay. So now we know how to grow, we know how to push forward the uniform measure on trees with n leaves to n+1. We can push that forward to grow essentially uniform three-connected quadrangulations, uniform three-connected maps, possibly with a local defect. And that gives us a growth rule, an explicit growth rule for squarings. So let me just tell you a little bit more about what that growth rule ends up looking like. I mean, I'm not going to describe the sort of random structure of the squaring near the point that we grow. I just want to describe what the growth rule, what a given step of the growth rule will be doing to the quadrangulation, for example. So remember that in the quadrangulation, we had these leaves that had attached into corners to form squares. So here's a quadrangle. Yeah? And when a leaf decides it's no longer a leaf because we've just grown at that leaf, it corresponds to some local rearrangement around the vertex of attachment on faces incident to the vertex of attachment. So it's something like this. Okay, so you now have two new leaves that are trying to close, and that sort of forces some other things to jostle around. But the nice property is that this is a purely local modification of the maps. Okay, this gets prettier when you describe what happens to the maps rather than the quadrangulations. So there's one of two possibilities, because somehow the Tut's bijection comes with a bicoloring of the quadrangulation, and it matters whether we grow at a white vertex or a black vertex. It corresponds to the primal or the dual of the associated map. If we grow at a facial vertex, a dual vertex, that corresponds to adding an edge that cuts a face of the map. Okay? And if we grow at a primal vertex, that corresponds to the dual operation, adding an edge that cuts a face of the dual map, or equivalently, taking a vertex of the primal map and sort of uncontracting it to form an edge. So these are the two growth operations on maps. And I'd like to just point out that in the squaring, okay, remember I said that edges have different aspect ratios if you give them resistances. Okay? So we can think of this edge that we just decided to add as having already been present but having infinite resistance. Okay? And an infinite resistance edge will have infinite aspect ratio. It'll correspond to a vertical line. Okay? And similarly, I can think of this edge as already having been present but having zero resistance. So that corresponds to a horizontal line. Okay? That's good, because horizontal lines correspond to vertices in my map. And vertical lines, by this rotation, correspond to vertices in the dual map. Okay? So what this operation is doing when you decide to, in the squaring, when you decide to grow at a given, let's look at a vertical line at a given facial vertex or dual vertex, is it says this vertical line should really be a square with aspect ratio 1. And so you can think of this vertical line as sort of pushing outwards against the neighboring squares, and they have to jostle and possibly resize themselves a little to make room for this square, but that square will eventually settle into its position in the map. Okay, and similarly in this picture, it's taking a horizontal line and stretching it vertically to form a square with aspect ratio 1. Okay. So this, in principle, means that you should be able to make some very nice video of this uniform law growing the squaring. And when I convinced Nicholas Levitt, my co-author, sorry, I should have said at the start of this whole thing, and my master's student to give me his code, then I'll try to write that. Okay, just a few last comments before I wrap up. we wanted we claimed that this sequence was converging in the local sense, this growing sequence of graphs. Okay? Well, let's also start with the trees and see how that pushes forward. A uniform binary tree with a given number of leaves is equivalent to a critical binary Galton-Watson tree conditioned on its size. And so as that size becomes large, it's well known that the trees converge locally to a limit, which is the sort of incipient infinite cluster on a binary tree. It consists of a single spine, which is equally likely to have left or right turns at each step in the planar setting, in which we are, decorated with IID critical unconditioned binary trees. Okay. And then there's a closure operation. Remember how we got to, from trees to quadrangulations, we attach leaves into corners. Okay? And if we want to claim that the quadrangulation stabilizes, then we need to know that that eventually stops happening near the root. Okay? This isn't a hard fact, but it's the thing that we need to show that Qn also stabilizes. And if Qn stabilizes, then it's not hard to use we got Gn from Qn just by Tut's bijection. It's not hard to see that, therefore, Gn will also stabilize. Okay. So I mentioned that the limit only has one accumulation point, and I think rather than rush through the math, I'll just tell you that I'll tell you what the math is that we use. We use some beautiful results of He and Schramm from some of the same papers that Asaf Nachmias mentioned the other day. Together with, so in order to use these results, we need the notion of vertex and edge parabolicity for our network. Edge parabolicity is equivalent to recurrence. Vertex parabolicity is a somewhat more subtle condition. But it turns out that combining them and using the result that Ori presented, we're able to show that we're able to verify the conditions of the theorem of He and Schramm that we need to prove there's only one point of accumulation. Okay, so there's lots of this work is based on two papers that are both publicly available. The first one has 6 open questions at the end. The second has 12. Lots of these are just essentially plagiarized because for any of these models, you can ask the same sorts of questions. So some of them are questions that you could ask about any one of these geometric representations of maps. Some of them are specific to this representation. Okay, like, for example, this limit squaring has an aspect ratio which is random. Okay, and it's not hard to show that it's a random variable with exponential tails. That's just saying something about the probability that there's the probability that there's a large resistance between the two endpoints of the root edge. When you remove that edge, should decay exponentially. It's also, because of the duality of, because if you take a uniform 3-connected planar map, and you take its dual, you get a uniform 3-connected planar map. The random variable w has the same law, which is the width of the square, has the same law as the random variable 1 over w. Okay? But I think that now I've told you everything we know about this random variable. It would be interesting to know more. It would be interesting to know more about the location of this accumulation point. It would be interesting to know if we can zoom in on the accumulation point and get some sort of a whole plane limit, or whether it's necessarily going to be degenerate. The analog of I think it was Ori's question about whether you see sort of macroscopic circles at a given distance from the root corresponds to asking about the circles that are cut by sort of a small ball around the accumulation point. How big can they be? And I think one of the advantages of this, of studying squarings, is that there's all sorts of quantities, or at least there are some quantities that you can access using explicit resistance calculations that in circle packings, for example, you only have implicit information about. You can calculate various things here via determinants. Circle packings have other advantages, but I think they're certainly both interesting. So I'll wrap up there, and thank you for your attention.
Yeah, so suppose you use a different algorithm to grow your binary trees, like Remy's algorithm, for instance. You say anything about what you get?
Well, you get the same distributional limit. It doesn't converge because you keep making local changes near the root. So it's possible that if you were searching for a compact, if you're searching for a limit more in the spirit of your question from the ICM proceedings, that would be a natural thing to do. Study something where the tree converges to the Brownian CRT. But I can't say anything about it.
So of course there are many things that we don't know about the random walk on the random planar maps, but can some of these questions be translated to some of these geometric questions, say the decay of the squares near the accumulation point?
Yeah,
Speed
so-
of the random walk be expressed?
so there are various, if you pick a second, one quantity that I think is very natural to study is essentially this. You take two, in the spirit of e to the GFF, you take two adjacent neighboring squares, and you'd like to understand the ratio of their sizes. Okay, so the difference, there are huge fluctuations in the sizes of the squares in this picture. You saw it. So the difference isn't the natural statistic; it's really the ratio is telling you something about the local fluctuations. Okay, and for example, if you take, it should be the case that if you take k independent samples from one of these large maps and look at these ratios of sizes, that converges in distribution toward a vector of independent random variables. Okay. That would be a first very weak step towards saying that this looked something like e to the GFF, because what we should see for a GFF on this map is that the product of these ratios around any cycle is 0, right? That's the constraint that comes from the geometry of the map. If you look at the ratios of sizes of squares corresponding to successive edges, you have to get back to the original size. Okay? So that product has to be 1, and if you take logs, that's saying that the sum of the logs of these ratios has to be 0. So the condition is that sums around cycles are 0 for the sizes of these squares appropriately described. But if you pick IID samples, you're not going to see the conditioning that comes from the GFF because you're going to pick squares that are far apart in the map. Okay? But even that I can't yet prove. It seems like the connection with random walks and electrical resistance should be useful, but I haven't found a way to do it.
So this is a question I learned from Stas Smirnov, and maybe they already have the answer, I'm not sure, but let me see if you know. So I guess if you want to show that the uniform spanning tree on one of these guys looks like the natural, SLE8 uniform spanning tree, then it's enough to show that in your embedding, when you do a random walk, it looks like Brownian motion. But the trouble with the walk is that when you do the walk, you know that the vertical coordinate is a martingale,
Yes.
just by construction.
Yes.
If you do a walk on the dual graph, then the horizontal component is a martingale.
Yes.
But you don't know that that
Indeed.
these two walks are close to each other, right?
Yeah, that's right.
So if you could show that the dual walk and the walk could be coupled to be close, then you would be done with showing that you get SLE8 in these guys. That's right?
I'm not sure if you'd be done to get SLE. I think I know the paper that you want to use. I'm not sure if it exactly applies to my limit object.
I think it's okay, but I guess my question is, can you actually say anything about
I've thought quite a bit
how
about.
the walk and the dual walk compare to each other? Are they close?
I haven't tried to couple them. I have tried to find some variant on this graph or on one of these graphs that's related to the squaring, which would yield something that was a martingale, but I haven't managed to find that. Yeah, but I haven't explicitly tried to construct a coupling.
Okay. Something about the sampling method that I'm not sure I understood is that you have shown us that there exists a flow that you can use to sample. But is it easy to compute such a flow and actually do the simulation?
When you have so it's not a uniform split. When you compute the split at the root, you can explicitly compute the quantities. They end up being, you see k on the left and n minus k on the right, then you should grow on the left with probability that's approximately the square of k over n. It can explicitly be done. I don't think because it's sort of recursive, it's not obvious how efficient it would be to just naively apply this method. Maybe there's a better way.
There are some other local growth rules which give you uniform trees. Like if you pick a uniform leaf and add a critical tree at that leaf, then that, in some sense, gives you a sequence of uniform trees, which might be interesting to. And that's very easy to compute, and that might be
right.
to apply.
Yeah, that's a good point. I think more or less if you can grow the trees so that the limit is correct, then all of the rest of the procedure is going to follow through. So.
Well, let's thank the speaker.